Hello everyone, welcome to High Performance Computing, Advanced Scientific Computing course. This is lecture 14, Solid Object, Finite Element and Meshes. Based on the outline, it is lecture 14 and we will focus on the finite element method. In the beginning of this lecture, let's have a review on the lecture 13. In lecture 13, we had a talk regarding attention mechanism, and we presented the fundamental of the attention, which is basically from the psychology and related to the cues, how the human attention to the some object, and it's converted to some mathematical and programming to be able to have more focus and attention on the specific object or data, and how we applying these mechanism of the attention in the sequential to sequential models. We determined the queries, keys, and values in the attention mechanism and how they are related to the cues. Then we presented two types of the attention mechanism, Bahdano and long attention, and we had very brief view on the architecture of these two models of the attention mechanism. Then we carried on the transformer architecture and how it looked like. We point to some specific features of the transformer that should has equal encoder and decoder layers, and how the data process on these architecture when it's received the input and then create the output. To see how it's working for the sequential data, we had data from the experiment in the turbulence flow, and we designed a transformer model to apply these experimental data and create a prediction for the short period of that data. We saw the capability of the transformer is remarkable, and it seems it's able to make a considerable prediction for such a phenomena in the fluid dynamic, because turbulence is nonlinear and random and really complicated matter. So, but in the transformer, we fed the model with these nonlinear data, and we were able to have a prediction of the velocity in turbulence flow. And we presented the result from these simulation. This is a short review of the lecture 13, and of course you have the recording and you have access to see more detail about that lecture. Now let's carry on the lecture 14. The outline in this lecture, we will talk about the numerical method in solid object and how they are look like and what the step we need to take to do these solution methods. And then we will have some finite element meshes discussion, and we will have some examples from the parallel computing in the finite element method for solid objects. Part 1, we will focus on the numerical method in solid object, and then we will have the second part as well. Finite element method, FEM, or finite element analysis, FEA, It's a numerical method like finite difference method that we had talked about the finite difference method in the lecture 8. However, the FEM finite element method is more general and powerful in its application, which could be involve multi-physics, complicated geometry, and boundary condition. In the finite element method, the domain is split to the number of the subdomain, and over each subdomain, the governing equation is approximated by any of the traditional variational methods or any method that is suitable. These possible methods, and we point to the suitable method, they are different and depend to the problem. We can choose the right one. The main reason we are seeking for the approximate solution on the collection of the subdomain is it because it is easier to represent a complicated function as a collection of the simple polynomial, as we can see here in this figure in this slide, how the main domain is divided to a small subdomain with different sizes to have a suitable method and approximate function for them. So this is the basic of the finite element method, and indeed among the well-known method in the numerical solution, finite difference method, finite volume method, and finite element method, the finite element method most powerful technique, because sometimes in other methods we are facing some limitation regarding the boundary condition, initial condition, the complicated geometry, but in the finite element method, it's capable to deal with these issues. In next slide, we will have some detail and we will talk about its capability. Why we are using the finite element method, or why in the solid object as well, similar to the fluid dynamic area, we are using the numerical methods. Of course, the best way to solve any physical problem which is governed by differential equation is to obtain the analytical solution. But there are many situations where the analytical solution is difficult to obtain. The region under consideration may be so irregular that it is mathematically impossible to describe the boundary. So sometimes we are facing the boundary issues. The configuration may be composed of several different material whose regions are mathematically difficult to describe. So sometimes in the solid object we have different material, like we can say the composite material is the example. So we have different properties of the material in the domain. It will be difficult to describe the boundary for this type of a problem. The problem involving anisotropic materials are usually difficult to solve analytically, as are equations having nonlinear terms. So we will facing the nonlinear term, which is difficult to solve. This is some of the issues when we are faced. We need to select the numerical method instead of the analytical method. A numerical method can be used to obtain an approximate solution when an analytical solution cannot be developed. All numerical solutions produce values at discrete points for one set of the independent parameter. The complete solution procedure is repeated each time these parameters change. So the numerical solution more desirable than no solution at all. The calculated value provides important information about the physical process even though they are at discrete points. So as we can see here, and we had this example on the lecture 8 and lecture 9 when we talk about the numerical method on the fluid dynamic area. With the numerical solution, we will have properties or values of the properties on the every single node or point, and with this collection we can have the properties or the solution for the domain. The finite element method combines several mathematical concepts to produce a system of linear or non-linear equations. The number of equations is usually very large. Sometimes we have 20 to 20,000, and maybe more requires the computational power of the digital computer. So this is the point here why we need or we have to apply the parallel computing or the HPC for the finite element method. Finite element method it's powerful. However, from the mathematical views, it's more difficult than other methods in the numerical approach. However, when we have a large size of the problem domain or many equations, the computational power is essential. Regarding the history of the finite element method, from some resources, there are mostly talking about the application of the finite element method officially when it's used for the aircraft and cars. However, there are not really official documents to say the origin of the finite element method. Because the basic concept have involved over a period of 150 years or more. The method, as we know, today is an outgrowth of the several papers published in 1950 that extended the matrix analysis of the structure to continuum bodies. Therefore, about its history in many literature and references, you can look on this example and the first published paper in this area. However, the most important feature of the finite element it's powerful, and we are able to solve most of the problem in comparison to other method that we have in the numerical approach. We talked enough about the finite difference method when we said it's applicable in the heat transfer and fluid mechanics problem, and especially it's working for two-dimensional of the problem, and when the boundaries are parallel to the coordinate axis. But when we have curved or irregular boundaries, and we can say the complex geometry, it will be difficult to apply the finite difference method to have the solution. Then we can say the finite difference method it's limited to some areas. We can use it widely. But when we look on the finite element method, for example, one of the procedure in this method is a variational method. The variational involves the integral of a function that produces a number. Each new function produces a new number. The function that produces the lowest number has the additional properties of the satisfying a specific differential equation. As you can see here in this slide, we can see this integral, how it looks like, which the numerical value of this function can be calculated given a specific equation of y equal to fx. The calculus of the variations shows that the particular equation y equal gx, which yields the lowest numerical value for the variational function, is the solution to the differential equation. So we can find the solution, and the boundary condition is specified at y0 and y on the highest level. Then this is one of the methods that is available. However, if we don't have the function, it will be difficult to apply this method. And also, as you can see, the boundary condition need to be specified. However, the variational method is the basis for many of the finite element formulation, but it has a major disadvantage. It is not applicable to any differential equation containing a first derivative term. Of course, this method is powerful and applicable, but we see here one of the major disadvantage and limitation that we have in this method. The next well-known method in the finite element method is weighted residual method, which is basically, as you can see, has an equation. The weighted residual method involves integral. In this method, an approximate solution is substituted into differential equation of the problem. Since the approximate solution doesn't satisfy the equation, a residual or error term results. From this error that we find in this equation, then we are looking to find the function or the equation of this error or residual. There are different methods to find this function. As you can see, here we can use this integral. The weighted residual method requires that this integral to be equal to 0. The residual Rx is multiplied by a weighting function, it's called Wx, and the integral of the product is required to be 0. There are a number of the function or method using to finding the Rx. You can see here we have the collocation method. It's using impulse function for the Wx. The subdomain method, it's each weighting function is selected as unity equal to 1. The another one is the Galerkin method, which is one of the well-known and powerful method to find the residual of the error term. Galerkin method uses the same function for Wx that were used in the approximating equation. This approach is the basis of the finite element method for problem involving first derivative terms. The another one, there is a least square method. The least square method utilizes the visual as the weighting function and obtain a new error term defined by ER. This error is the minimized with respect to the unknown coefficient in the approximate solution. The least square method has been utilized to formulate finite element solution, but it is not as popular as Galerkin method and the variational approach. So as you can see, the Galerkin method in the weighted residual method and the variational approach are the most well-known method in the finite element method and can solve the problem in the good manner if they are suitable for the condition of the problem. Of course, in the finite element method, to do the solution and discretize the domain of the problem, we need to take some steps. The first step is discretize and select the element type. In this regard, we are facing a definition. It's called aspect ratio, and if we look here in these few examples, there is a different dimension of the domain, and the aspect ratio is defined by the longest dimension to shortest dimension. For here in this example, we can see this is the longest answer. So when we doing the discretization, is depend to how this ratio is working. Here you can see the ratio is 24, 6, 1.5, 3.6, and 1.1. So it depends to the size of the element with respect to this aspect ratio. In this figure, you can see the curve of the different methods. This number 1, 2, 3, 4, it's related to this example, and we can see how it look like when we choose different uh, aspect ratio. When it's going upper, and we have larger of the aspect ratio, how far it's getting from the exact solution. So it's important to have a right selection for the ratio of the element. And here there are a few examples about different cases with aspect ratio with different shape of domains. According to the previous slide, we talk about the aspect ratio, and we can see here in a different example with different domain how the element is working. In some areas, we need to have a fine element to be able to solve the problem correctly. As you can see here, the size of the element and the shape of the element near to this hole in this domain has a different size to the other element. So there are some important points we need to take to the consideration when we are doing the meshing in the finite element. Here we see this example, the plate with hole on the plane stress. As you can see, because it's symmetric geometry, so we can solve these only a quarter of this domain, and then we have solution for all of these domain. These are some technique and some requirement to know to this type of solution. And there are another example of the meshing, as you can see here, depend to the forces, if it's distributed or if it's a concentrated load, and what it look like, the shape of the domain. If there is a difference of the section, here you can see the section is different, or we can see the thickness of this. And also about the material, when we have different material, we need to specify the boundary and domain. So there are many issues we need to pay attention to doing the meshing in the finite element to have a correct solution. When the type of the element or mesh is chosen, then the second step is selecting the displacement function. As you can see here, we have different element or displacement function for this element. As you can see, there are two nodes line element and high order line element here. So it depends to the problem. Also for the two-dimensional problem, we have these different element with different number of the nodes. High orders also it's available. Regarding the 3D, also as you can see here, for the 3D mesh we have different and also the high orders element with intermediate nodes along edge, as we can see here. And also we have axisymmetric, triangular, and quadrilateral element used for the axisymmetric problem. Here, this is two examples of this element. So depend of the problem and dimension of the problem, we can apply these different element which is determine the displacement function. The step 3 is defining the strain or displacement function and stress or strain relation here. Derive the element stiffness matrix and the equation here, and here how the matrix look like. Assemble the element equation to obtain the global or the total equation and introduce the boundary conditions. In step 6, solve for the unknown degrees of freedom or generalized displacement. And at step 7, solve for the element strain and stresses. And then step 8 is interpret the result. However, the discussion and detail of every step has a long discussion. Of course, the finite element it's as a course, and to know the detail about this, maybe you need to take one or few courses to be able to understand all detail and the procedure. Of course, if you are interested, you can go through the references available for these methods. In this lecture, only we are going to have a review, and then we will talk about the parallel computing, how can help us in this method. For example, here, as you can see, this matrix for 3D problem, this matrix is mm, really large and extensive matrix, and to solve it, of course, we need the parallel computing to be able to do that. Regarding the finite element method, it has a wide application. It can be used to analyze the both structural and non-structural problem. We can say we have the typical structural areas like the stress analysis and stress concentration problem. There are buckling, like column of frames. There is a vibration analysis, impact problem, and regarding the non-structural problem, there is a heat transfer, a fluid flow, and distribution of the electric of magnetic potential. So as you can see, the finite element method is a numerical approach. It could be used in both main area for solid object and as well for the fluid object, which in the fluid we have the gases and the liquid, and also in the solid object. So its capability or its application broadly, and however, depend of the type of the problem, depend of the condition of the problem, we should choose of these available method in the finite element method. Here are a few examples to visualize its application. You can see it could be applied for some, maybe we can say 2D simple domain. However, it could be complicated geometry, and also for this type of the problem with nodes. And you can see here the complex problem for the wind turbine, and here in the medicine application. So it's the finite element method is broadly applicable, and it could be used to solve many type of problem. However, for large problem and 3D problem, without parallel computing, it could not be used easily, and sometimes it's impossible because of the computation. We talked about the different available methods in the finite different method, the finite element method. Here there is an example to present its difference in the variational method, Galerkin method, least square method, collocation method, and subdomain method. As you can see, here is the governing equation, differential equation, and boundary condition for a simply supported beam with concentrated end momentum. And when it's solved with a different method, we can see the percent error in its reflection, how it look like. Of course, when it's close to zero, that means the error is lower. You see the variational method, Galerkin method, and least square method have a best condition than the collocation method and subdomain method. However, it depends to the place of the solution. These error for 5 approximate solution we talked before, and we can understand which one has a less error and better error. However, it's not possible to state which method is the most accurate. The error depends on the approximating function and the equation being solved. Percentage error curves for different methods given in this figure indeed provide us this information that which one could be selected for this type of the problems. One of the another well-known method in the finite element, it's the potential energy formulation. For some time, some type of problems that they are in the category of elasticity, plate and shell structure, it could be solved by this method with called potential energy formulation, as you can see in these slide and these pictures. In some structure and object, the uh, object composed of the some plate and shell structure, and we have some material with elasticity behavior. So from the energy formulation in this method, it's possible to solve this type of problem. This is the last point we presenting here in this part, and this is the evidence to say how the finite element has a power and capability to deal with a wide range of the problem in the solid and fluid area. We are finishing the first part of this lecture, and here there is a video. It's presenting the application of the finite element method and how it could be applied to develop some industry. I recommend you watch this video, and we will back shortly to continue on the second part of this lecture.